Okay. So, good evening, everyone. Today is our mm, lecture 10 of Introduction to Commutative Algebra and Algebraic Geometry. Uh, Today we'll be doing problems related to Jarisky's problem, Jarisky topology, and problems regarding those, and problems regarding Hilbert Nahl-Stollenger's will be doing after we are introduced integral extension in the last class. So in first class, in first TA session, we introduced uh, uh, some results or introduced Jarisky topology, but those I will be doing in full generality, and yeah. Okay, so give me some time. Mm. So today we'll be doing mostly problems from chapter 1. Uh, okay, so in a okay, since I don't have the book with me right now, I will be making some copy paste of problems. Mm. Okay, so 15, this problem, this uh, constructing a Jarisky topology on the prime spectrum of a ring, it is done. Okay, I will be doing this. Okay, so let me paste it here. So this will be our problem 1. Yeah. Okay. So now first two things, that is this and this, uh, they are quite trivial, right? Draw means just find out the prime spectrums for these things. So solution, note that uh, note that spec of Z are all the prime numbers. P is prime in Z or P equals to 0. That is of the form 0, 2, 3, 5, like this. Now you all know that R is a field, right? Real number is a field, and a field has only trivial maximal ideal. That means it has only trivial ideal, that is zero ideal. So spec of R, I'm pretty sure it won't be asked any exam, but from third I think it will be slightly challenging, because spec Cx is also, you know, that it should be ideals of the form principal ideals of the form x minus a, where a is coming from C. Okay, I will do it. Actually, the most challenging thing is spec of zx, but yeah, it may take half an hour or 1 hour, but I will do all the things. For spec Cx, note that C is a field, hence Cx is a principal ideal domain. That means it is a PID. So later on I will denote this as PID. Thus, let A be a prime ideal, right? Now, to check the irreducibility of F, we first assume F is reducible. Then F equals to GH for some GH belongs to Cx thus F is not prime. I mean, since F is a polynomial with minimal degree in F and G and H has a degree less than F, so both G and H does not belongs to F, so yet F belongs to F, ideal generated by F, so it is clear that F is not prime. Now if degree of F equals to 0, then F equals to 0, otherwise F should be 1, right? Because otherwise it would be a unit element, and unit element produces trivial ideal, right? So you're done. If degree of f is greater than equals to 2, then f splits into linear forms. Since she is algebraically closed, so then f would not be a prime ideal. Right? So we are only left with one choice, that is, hence only non-zero prime ideal occurs when f is of the linear form x minus a. Thus, spec of cx should be x minus a coming from C union 0, right? Now, one thing to notice is that it has a generic point, right? Means it has a point whose closure is the whole set. I will be coming to that, which is closure and everything, but for now on, let's leave it. Okay. Now we will be coming to spec Rx. Now, for spec Rx, also this is a PID, right? Also Rx is a PID. Hence, this is a standard result from algebra 2 or ring theory. F is prime ideal if and only if f is irreducible and there are uh, two irreducible polynomials with respect to degree f is linear form x minus a or f is degree 2 polynomial f equals to x square plus px plus q such that p square minus 4q is less than 0. So what I'm really trying to say is that in a polynomial ring over a real field, you know that there are only two types of irreducible polynomials, right? And these are coming from your 11th and 12th degree knowledge, 12th class knowledge. That is, we cannot split a polynomial into of this form into uh, two linear terms if their determinant is negative. And why we cannot get up to third or fourth? This is coming from the general field theory or field extension. That is, complex number are like extension field of degree 2, and that is an algebraically closed field. Also algebraic closure of this R. So if you have a irreducible polynomial and if you take a field extension of that over R, then you will be getting a field of degree 3 or dimension 3, right, as a vector space. But that is simply not true, because its algebraic closure has dimension 2. So yeah, I'm saying that of degree 3 or bigger than degree 3. Hence, we can think it as a picture of R with big points 0 and PQ R2 P square minus 4Q less than 0. So you are seeing that it's kind of the uh, uh, like it has a copy of R, this and this. So these are responsible for this. 0 is 0, that is a prime ideal, and these are responsible for this. These are also important for the as a PhD interview questions. Okay. For now, okay, I should mark. Now Zx is little trickier because Z is not a field, so Zx is not a PID. So you'll see how we formulate this Peck diagram. Now for this, we'll take two diagrams, two maps, phi from Z to Zx and psi from Z to Z by P. So it's a field because for each P equals to 0 or prime. Then it gives us a commuting diagram spec of kp x. Your kp is nothing but the field, that is z by p. Spec of zp, from here to spec of zx, spec of z. So how are we getting this so your kp is a residue field of p. So that means it is of the form z by p, because z is an integral domain, or to say commutative ring with identity. So if you slash it with a maximal ideal, that is if you take quotient with a maximal ideal, then you will be getting a field, and that is called a residue field. And how are you getting this spec structure? uh, okay, we are getting the diagram from z to zx, simply quotient map uh, kp to kpx. So you know that this commutativity is kind of trivial and routine checking. So you are getting the diagram from this map, and if you take the spec of this diagram, it will be reversed, right? Because taking spec is direction changing between the two categories, like affine schemes, or how would I say this, spectrums, and the category of spectrums, and the category of finitely generated K algebra, or like rings. Okay. Now okay, this will be little advanced than I imagined, but one can see that your kpx is nothing but zx tensor kp z, that is spec of kpx is a pullback of two maps, say this is phi star lower star coming from phi and the psi lower star coming from psi, two maps phi lower star and psi lower star. If phi not equals to 0, then Kp is Zp. I have already said this, so okay. If phi not equals to 0, then we have Kp equals to Zp. And it should not be the Z by P, it should be Z localized at P. But yeah, and if should be it should be Z by P. My mistake. Should be ZP. Yeah. And now if p equals to 0, then Kp equals to Q, because Z localized as at 0 is Q, right? Now hence spec of Zx would be P comma F, where your F is coming from Zx and irreducible at Zpx, where P is coming from spec of Z. Union F belongs to Zx, irreducible over qx. So yeah, you are done. So basically I thought it would be easier for me to make you understand this, but it involves some techniques that is not here or hasn't been learned in this course, so I am carefully uh, avoiding this. The note I have with me is involves the pullbacks of the maps, and I don't think I will make you understand in this short time. Okay, okay. So you are done. Okay, we will be going to our next problem. That is this one. Okay. So try to get familiar with this problem. Then we'll be doing this after 5 minutes. So in the last one, residue field being ZP is it's localized at P, and KP should be uh, Z by P, because it should be ZP uh, VZP. Okay. Actually, it should be ZP by S inverse P, which is isomorphic to Z by P itself. So from that, I think I'm right. So it's slightly it's mistaken. Yeah. Now I think it's fine. ZP and yeah, yeah. Okay. Now we'll be seeing an interesting result from this. I hope you are now familiar with this uh, question as of now. Solution. So for an element f of a, except denote the complement of VF in X, that I have told you earlier in spec case. So these are all open sets. I think I have used this result also, that excepts are the basic open sets. Sorry, I did not do this, prove this earlier. Okay. Uh, yeah, so first we will prove that these are the basic open sets. Basic means uh, like these are the minimal open sets in the, these are the building blocks of the topology. Like any open set are the unions of these open sets. That means if you take any element and any open set around them, they are at least one of these elements content between that open set and the element. So to see except from a basis of open sets for Zariski topology, first of all they cover spec. We have to see that. So just take f be a unit, that means f is invertible. Then your xf equals to vf complement, that means v1 complement, and you know v1 is phi, right? So phi complement, that means your spec A. So at least you know that this covers the whole set, this type of sets. Thus we need to check that for any two open sets xf and xg has non-zero intersection, and if p is in the intersection, then there exists xi containing h and PTO and contained in the intersection. To get this, note that, so what I have just written is that to prove something is a basic open basis of open sets, it is enough to prove that it covers the whole set, and for any two open sets it has non-empty intersection, and this intersection is also a basic open set. That means you know that any two opens intersection of any two open set is intersection open, and we have to show that that open set is also a basic open set. Okay, to get this, note that P do not contain F and G. So take except G, that means the prime ideals that do not contain this product. Then from VF comma VG is contained in VFG, XF comma XG containing XFG, which implies XF intersection XG contains except G. Also, since P do not contain F and G, neither does FG. Otherwise, from the prime ideal property, one of F and G should lie in P. Contradiction, hence P belongs to except G. So what we have shown is that any two of these sets intersects non-trivially because an element is contained in both of them, and also an element of type X FG is contained in both XF intersection XG. So we have shown that these kind of open sets are the basic open sets. So the first part is done, that is from a basis of open sets, that part is done. Now we'll check all these properties up to 7 one by one. So yeah, coming to the first one, we already show that XFG is contained in both XF intersection XG. Let P belongs to XFG, then by the same argument P does not contain F and G. Thus, P belongs to XF intersection XG. Thus implies equality. Now for the next one, saying that this is kind of an equivalence statements, that is XF equals to MT if and only if F is nilpotent. Nilpotent means the some power of F should be 0. Suppose XF is empty. It is equivalent to say that every prime ideal contains F. Also it is equivalent to say that F is in the intersection of all prime ideals, that is nil radical. What I'm trying to say is that xf is empty means what? That vf is the whole set, right? So f is contained in the all prime ideals, and if f is contained in the all prime ideals, then f is contained in the nil radical. That means what? That f is a nil potent element. Now for C, that if again if xf is the whole set, then f is a unit, and it is clearly similar, but yeah, xf equals to x, that means what? Vf is empty, that means no prime ideal contains F. This is equivalent to say that F is a unit. If F is unit, then no prime ideal contains F. So the first argument is coming from this, and conversely if F is non-unit, then if is proper. Thus there is some maximal ideal containing F. So this is a contradiction. Now for the fourth one, if you are saying that this one is coming from the Hilbert-Nullstellensatz, right? That if Vf and Vg are equal, then their radical ideals are equal. So I'll just write it in as one liner. Xf equals to Xg if and only if Vf equals to Vg if and only if Rf equals to Rg. Hilbert Nernst telling this. So yeah, this is a good exercise from this. Finally, we have found an exercise. Okay, so for the fifth one, X is quasi-compact. You know what is a compact set, right? That is that every cover has finite subcover. And in algebraic geometry, we just say this as a quasi-compact set. So you can say it as a compact also, but yeah. Um, these are quite similar. I find no difference, but yeah. So this will actually come from the uh, uh, Noetherianness because uh, uh, and the finite sum property of this. But yeah, I'll be doing this. To see this, let ui be an open cover of spec A. Then actually using basis we can find more finer open cover consisting of excepts say except coming from J for some index set J. So this implies what? This implies spec of A equals to union of xf. A belongs to J, right? Union Vf complement A belongs to J, intersection of belongs to J Vf complement. So by De Morgan's law, that is the union, the complement of the union should be intersection of the complements. So again, this is coming from the 12th standard, which implies intersection of Vf should be empty to J. This implies so this is nothing but V of J, right? So this implies J should be 1 Hence 1 should be to 1 to n AJFJ for some FJFJ and AJ of A so these FJs are coming from this set, right? Because F was generated by these things and all the elements are finite sums thanks to the algebraic property. So this implies that intersection j equals to 1 to n VFJ should be V of union FJ j equals to 1 to n is empty, where first equality okay, I want to refer to the references. Okay, this implies spec of A should be intersection j of 1 to n V of Fj to C, and it should be j equals to 1 to n except, which is a finite subcover. So we are done. So this is so we have shown that the spec is quasi-compact. So we will show that the not only that these X shapes those are also quasi-compact, but this is a one-liner. Once you know that X shape is spec of AF, so X shape is quasi-compact. This is one proof, but there is also another method. Okay, think of another method. Then we will be. I will be showing another method also. Also this thing that an open subset is finite union of these sets. I think these two. Okay, so maybe we'll do another method also. So another method to see that each X shape is quasi-compact. Let X shape I next to I be an open cover of X shape. Then X shape equals to union of II X shape I intersection X shape and union of to I X F Fi. Thus for simplicity replace Fi with Fi so that assume X shape union of I X shape I this implies VFC from I VFI C to intersection I of I VFI C. So this implies VF equals to A of I V of I would be V of union of Fi belongs to I. This implies R of F should be R of Fi. I belongs to I, capital I. Thus, f to the power n equals to j aj fj for some finite subset j of I for some to capital N. Thus, for any prime ideal P belongs to capital I Fi to the power n to I of I J Fi implies to the power n to p. Thus, F belongs to P by prime property. Hence, V of F is containing J this implies V of Fc should be except V of I of J Fi C J of J V of Fi C equals to union of Fj C is to Fj x Fi. So this looks hideous, but if you look carefully, that these are all like trivial steps. Thus, X shape is contained in union of I of J Xi containing I of I Xi is to X shape implies X shape equals to union of I of J Xi. So X shape has a finite subcover for any open cover. So yeah, so we have another one, that is the last one, that in open subset of X is quasi-compact if and only if it is a finite union of sets. So yeah. Maybe this will be our last problem. I'll see if I can do more. Let O be an open subset of X if O is a finite union of sets except say O equals to union of JJ except J for some finite index set J, then finite union of compact set is compact. Conversely, suppose O is quasi-compact, then since X is a basis of given topology and O is open, we can say O equals to I phi for some index set I, and note that it may be infinite also. Thus xfi I belongs to capital I is an open cover of O, hence we can take finite subset J of I such that O is contained in I of J xfi from quasi-compactness. Hence J xfi xfi store implies equals to I of J xfi a finite union sets now. So we are finally done of this big problem. Now we can we'll be doing this problem, that is 18 from Athiya McDonald chapter 1, and then we'll be wrapping up for today. But in the next class I'll see what I can do. Maybe I will do some problems from third chapter. There are some beautiful Zariski topology problems that I did during my grad course. Yeah, this should be 3. Maybe I should erase this number so that it is less confusing. So yeah, try to understand the problem for 5 minutes, then we'll be doing this. Okay, so this will be our last problem. uh, so yeah, you can see the convenience here that for a prime ideal p uh, for a prime ideal of a from when we denote it as a point of x from capital X, we denote it by px. It's the same thing. So yeah, uh, so for yeah solution, yeah, if px is maximal, then vpx equals to small x. If there exists a prime ideal containing maximal ideal px, then by maximality it should be px itself. Hence, if px is not a maximal ideal, there exists a maximal ideal M containing px properly. Thus, M vpx, which implies px, which is a contradiction. Hence, px is maximal. Now, for the second one is saying that any the closure of any point should be the set of all prime ideals containing that prime ideal, right? So these are all like easy doing, but I'll still be doing. This contains x and is closed. Thus, vpx x bar. Conversely, x bar equals to ve for some subset E. Then vpx to v implies px containing E. Thus, for any prime ideal P containing Px, it contains E. Thus, Vpx is to Ve is to square. So we are done. Now for the third problem is saying that if an element is contained in the closure of a set, then the ideal condition should be reversed. Again, this is also a like chain of observations. This is x bar. Then you know that y should be contained in V of Px, right? Thus, Px is contained in Py. Now, conversely, if Py contains Px, then Py is in Vpx equals to x bar. And for the last one, if y are distinct point of x, then either Px is not contained in Py or Py isn't contained in Px without loss of generality. Assume Px contained in Py, then y belongs to x bar. Thus, x minus y is an open set containing y but not x. Okay, so up to this point have done several big problems, but the good thing about these problems are like these are the building blocks of Zariski topology. So first we have studied some examples, then we have studied several properties, and in the next class we will be studying these kind of problems, that is what is irreducibility, and I have done this problem. So direct product thing, yeah, okay, let's see how much we can do in the next classes. Okay, we'll be doing these two problems, that is affine algebraic varieties and these things. This will be interesting. Okay, so keep studying these things, and let me know if you have any problem. So yeah, we will be finishing early today. Okay.